Hi everyone, my name is Julián Fresán, and today I want to tell you a small story that begins with something very classic, Prüfer sequences. We usually use Prüfer sequences as a convenient encoding of trees, almost like a compression format, but what if instead of using a single encoding, we look at all possible permutations of a Prüfer sequence and how they interact? This will give us the definition of a new graph, the Prüfer sequence graph, and that graph is surprisingly structured and surprisingly rich. And that is the object of this talk. So this is a joint work with Tania, Aldo, Osvaldo, and Maximiliano, who are students that participated on a workshop called Tomate that we made in Mexico. And just to align our vocabulary, we're going to talk about trees. A tree is a connected graph with no cycles. And for example, the first one, even though it looks like a tree, it's not a tree because it contains a cycle. The second one, it's almost a tree, but it's not connected. So that one is also not a tree. But the third one is a connected graph with no cycles. That graph is a tree. So the Prüfer algorithm is a quite nice algorithm um, that enables us to transform a tree into an integer sequence. And it's quite easy. We remove the leaf with the smallest, if we have a tree, we remove the leaf with the smallest label and append to the sequence the only vertex that was adjacent to the removed leaf because the leaf is a vertex of degree 1, the only neighbors is well defined, and we repeat this process until there is just one edge left. So let's try an example. We have this tree, so we look to for the leaf that has the smallest integer, and we append to the sequence that right now is empty. We append its only neighbor, that is the tree. Then we look to the next leaf, we delete that edge, and then we look for the next leaf that has the smallest label, and we append its neighbor, so it's 5. And we continue to do that. It's 1, and then it's 1 again, and then now the vertex 1, it's a leaf, so we append with 3, then vertex number 3, and the process finishes when we have only one edge. So the result of the process of this process is the Prüfer sequence. And this is classic material, of course, but we will see it in a new role because there is a very interesting property that Prüfer sequence have. Uh, and that is that the degree of vertex I minus 1 is exactly the number of times I appears in the Prüfer sequence. This is nice because the Prüfer sequence is not just an encoding, but it is also a counting device. Then this connection will matter later when we somehow perturb a Prüfer sequence. So let's see an example of this. Here we have a tree, and here we have the degree sequence of the tree. Observe that, for example, the first entry of the sequence, it's is the one corresponding to the degree of the vertex 1, that is 7. The second entry, it's corresponding to the degree of vertex 2, and so on. And here we have the Prüfer sequence associated to this tree. So, for example, if you look to vertex 1, the degree of this vertex is 7, and the number 1 in the Prüfer sequence appears 6 times, 1 less than the degree. That also happens with vertex 2. Its degree is 4, and it appears 3 times in the Prüfer sequence. Vertex 3, whose degree is 3, and it appears 2 times in the Prüfer sequence, and vertex 4, that has degree 2 and appears just one time. As you can observe also, every vertex of degree 1 does not appear in the Prüfer sequence. So that is really nice because we will now define the Prüfer sequences graph. And given a Prüfer sequence of some tree, we will interchange two consecutive labels. For example, if we have I and in another place I plus 1 or I minus 1, we will interchange the order of these two labels and preserve everything as it is. So, for example, if we interchange the label I and the label I minus 1, we will obtain this new sequence that has everything equal, but I and I minus 1. They just swapped. And we will call this the swap of the graph. But we could also interchange label I and label I plus 1, like in this case, and everything else remains exactly the same. So with this idea of this swap, let's build a graph where the vertices are the different permutations of the elements of a given Prüfer sequence, and the edges will be exactly the ones we obtained performing the swap. That is, we will join two vertices whenever one can be obtained from the other by performing this swap over two consecutive labels. So, for example, here we have a path graph with 5 vertices, and its Prüfer sequence is 2, 1, 3. So we will the vertices of the Prüfer sequence graph will be all the 6 permutations of the elements of this sequence. That is 2, 1, 3, 1, 2, 3, 1, 3, 2, 3, 1, 2, 3, 2, 1, 2, 3, 1. And say, for example, that we have this sequence, the 2, 1, 3, 1. So if we perform a swap like this, we will interchange the 2 and the number 2 and the number 1 because they are consecutive numerically consecutive, and we will interchange them. So here we have 1, 2, 3. That means that the sequence 1, 2, 3 will be adjacent to the sequence 2, 1, 3. So we can build this graph with where the vertices are all the permutation, and we look for these adjacencies. And here is the associated graph. And here also appear all the trees corresponding to that sequence. Something that is important is as the degree property of proper sequences. In all these trees, the degree assignation or the degree, well, the assignation of degrees will be always the same. For example, vertex 1 has degree 2 in all these trees. Vertex 2 also has degree 2. Vertex 3 also has degree 2 in all these trees. And 4 and 5 will be leaf vertices in these trees. So we're going to look in the search space of all the fixed degree trees, but through instead of looking at the trees, we will look at the Prüfer sequences of these trees and all the permutations of a Prüfer sequence of that of a tree with certain fixed degree sequence. When we permute that Prüfer sequence, we will obtain any other tree that has that degree assignment. So this is the graph. For example, in the top right tree, we can see that we swapped labels 2 and 3 to obtain the topmost tree. So we do that for every vertex, and this is the proper tree sequence. Here's another example. Here is the double star. So this is the sequence of a double star where vertices 1 and 2 have degree 3, and every other vertex is a leaf. So this is the beautiful graph that can be obtained by this. And this is the sequence for a star. So in fact, the sequences on a star are quite nice, behave quite nicely and look amazing. So for any tree, we will construct this its Prüfer sequence and then the Prüfer sequences graph. And well, we decided to study many of the properties that these proof sequences graph have, and they have we got many nice results. For example, we were able to calculate the order, the regularity. It's a regular graph, and the size of the graph, the number of edges. Well, that one is obtained by the handshaking lemma and the order and the regularity. But there is really nice structural properties like factorization, connectivity, and Hamiltonicity that I will talk a bit of it. For example, when we're talking about factorization, we mean something like we can obtain the proper sequences graph looking into subgraphs that have a certain property. For example, if we fix in the first entry of the sequence the number one, we will obtain every sequence, like here in this example, we will obtain all the sequences. Well, we'll get all the sequences with number one in the first entry. And that will correspond, the subgraph obtained by the looking for all the sequences with the green one in the first entry will correspond exactly to the Prüfer sequence graph of the remaining three entries, that is the 213 Prüfer sequence graph. On the other hand, if we fix the number two on the first entry, we will obtain the Prüfer sequence graph of 113, that it has no adjacencies because 3 and 1 cannot be swapped. And finally, the blue one that fixes on the first entry the number 3, we will get the 112 Prüfer sequence graph that is a triangle. So this is one factorization. It's quite nice and quite useful because it let us like do something by induction. We reduce it to a previous case and assume by induction hypothesis the whatever property we want works, and then we try to get back when applying the induction step so that the property still holds. Another factorization we have is this one. Instead of fixing the number one, two, or three on the first entry, we will look where a certain number appears. For example, instead of here we are gonna look for the number three, and the three can be in the first entry, as in the blue vertices and on top left of the image, or in the second one at top right of the image, on the third one in the bottom right part of the image, or the fourth entry in the bottom left part. And as you can see, when we fix that entry, the corresponding subgraph will be the subgraph of the 112 prefer sequence, and that one is a triangle. So it's this factorization idea can make us like think of it's like the structural backbone of the whole story, and it's like the general idea of this factorization is that every part, like the blue, the red, or the green, or the yellow, correspond to a block, and the entire graph can be seen or understood as somehow an operation or a product of these blocks. And once you see this composition, well, the rest of the properties begin to unfold naturally. And they are really, really uh, natural because, as I've said, we assume by induction hypothesis that some property behaves well in the subgraphs and then try to prove it in the inductive space, and that it's exactly what happens with the connectivity. When we the connectivity is almost immediate if each block uh, is connected by induction hypothesis. We fix the last entry so that number A appears, number B plus one, and so. And if each block is connected by induction hypothesis, we just need to find like a bridge between each block, and then we can get a path linking every two vertices. And that's exactly what we did. We start with the vertex V, then we find a bridge connecting that component that has vertex V on the last entry to a component that has B plus 1 in the last entry, and then to a component that has B plus 2, and so on, so until B plus K. And for that, it's important that every number appears on a Prüfer sequence from B to B plus K to the end. So for that, we just need that the tree is labeled decreasingly by degree. That is, vertex 1 is the one with the larger degree, vertex 2 is the second largest degree, and so on. And if that happens, this graph is always connected. So, for example, here it's like we look at those subgraphs, the triangles of each color. Those subgraphs are connected, and then we just find these bridges to connect to each other component. In fact, we just need one bridge to connect to the next components and so on. And that's the proof of the connectivity. For the Hamiltonicity, well, we were just able to obtain the Hamiltonicity of paths. Nevertheless, almost every example that we made, it's Hamiltonian. The corresponding Prüfer sequence graph is Hamiltonian, but sadly, we were not able to prove that. But we were able to prove it for paths. So the Prüfer sequence of a path is a permutation, because each vertex appears just one, with the exception of the leaves. So it's a permutation, and we could construct a Hamiltonian path using the factorization. And the general idea for that is that we fixed a certain entry. Well, we keep moving the certain entry for a certain label in all the entries, and in every block we assume that the graph contains a Hamiltonian cycle, and then we build like a bridge. See, for example, this one. This is the block that had, these are 4 blocks. This one has a Hamiltonian cycle, like here. These 2 blocks have a Hamiltonian cycle, and the first one correspond at all the Prüfer sequences that contain number 4 in its first entry. The second one to all the Prüfer sequences that contain number 4 at its second entry. By induction hypothesis, it has a Hamiltonian cycle, and then we can find these 2 pink edges that will connect these 2 Hamiltonian cycles, and we delete like the corresponding edge in each cycle and swap them for, or interchange them for these pink edges, and we obtain like a Hamiltonian cycle between the first block and the second block. And we prove that we can do that for the third block and the fourth block, like this. So we obtain a Hamiltonian cycle over all the graph. And well, that's all I wanted to tell you. I hope you liked this talk, and any comments or doubts you can write. This is my email and my YouTube channel, where I have many videos in Spanish of mathematical modeling and some talks and so on. Thank you very much.